Hello everyone, my name is Tao Liu, and let me introduce our team's work, the Excellent Speaker Diarization System for the Conversational Short Phrase Speaker Diarization Challenge 2022. This is a joint work from Excellence team and AI-Speech company. This is the main content of our presentation. We will introduce our work from four aspects: overview, model selection, model architecture, and conclusion. The main content for each part is shown in the subtitle. In the first part of our presentation, we will briefly describe the dataset and the metric used in this challenge. In this slide, we will list all allowed datasets. We utilize all the data in our system, which will be discussed further. The speaker verification dataset, usually used for speaker embedding extractors in Diarization, contains two datasets, vox syllable and scene syllable. The total number of speakers is over 10,000. For augmentation, we utilize commonly used noise dataset Musen and add room reverberation to audios. The organizer of this challenge provides a CSSD dataset for participants. This dataset is converted from the magic data RAMC dataset and contains 108 hours. CSSD provides additional 19 hours for the final evaluation. CSSD is a newly proposed dataset, which is short for Conversational Short Phrase Speaker Diarization Dataset. This dataset contains four parts: training, development, testing, and evaluation. The second and third column shows the duration and speech occupation, respectively. The speech occupation shows plenty of non-speech segments, and voice active detection is important in this challenge. We also list other features here. CSSD is a conversational speech dataset and its language is Chinese. The total number of speakers is 663. For each dialogue, two speakers talk in turn, and the duration is long. Most of them are around 30 minutes. Lastly, this dataset has no overlapped regions, so we don't need to tackle overlapped speeches. For short phrase analysis, we also count the segment distribution for CSSD. This graph is the segment length percentile chart, also called the volume plot. For each dataset, the volume plot shows the first, median, and the third quartile. AMI is a meeting scenario dataset, and Vox Converse is a TV news scenario dataset. Core Home and Die Hard 2 has plenty of conversational speech, and CSSD has a similar shape to them. This is consistent with the fact that the scenario of CSSD is conversational speech. Besides, the first, median, and third quartile are higher than those two datasets, meaning CSSD also has much longer utterance. Those features will guide our model selection part. After analyzing the dataset, we briefly introduce the evaluation metric in this challenge. The diarization error rate, short for DER, is a commonly used diarization metric for this task. It accounts for salon, missed speech, and speaker confusion errors from the duration aspect. However, errors caused by short phrase often overwhelmed by longer ones because the short duration has a small length. In this challenge, CDER alleviates the problem by evaluating from the segment level. CDER is the result of unmatched segments to the reference segments. This is one sample to illustrate the CDER calculation pipeline. The pipeline contains three major steps: merging, optimal mapping, and IOU mapping. In the first step, CDER merges the adjacent segments with the same speaker. This step can avoid arbitrary segmentation of the hypothesis. In the second step, CDER operates the optimal mapping, the same as the other diarization metrics. In the third step, CDER searches all matched segments with IOU under 0.5, and other segments are considered as unmatched. Finally, we got the final result with this formulation. After analysis of the pipeline, we found that CDER is less sensitive to the boundary of inner segments because of the merging operation. And CDER will deteriorate if there are false alarm or missed speakers. Those findings will guide our parameter fine-tuning stage. In the model selection part, we analyze two systems, EEND and modularized system. EEND is an end-to-end neural direction system and can be directly optimized on the training data, CSSD dataset here. Modularized systems, also called clustering-based systems, have several modules, VAD, embedding structure, and clustering, which is trained or optimized independently. Although EEND can make the best of CSSD dataset, we still choose the modularized system for three primary reasons. First, EEND requires large amounts of data. 180 hours of CSSD dataset is not enough, and EEND requires 1,000 or more hours for training an efficient model. Besides, other labeling Diarization datasets are not allowed to use here, so we cannot only fine-tune the pre-trained models on CSSD. Second, the original transcript contains ambiguous labels like unintelligible words or dialects. This part includes 4 hours, which may affect the training process of EEND. Last, most duration of CSSD recordings are around 30 minutes, and EEND cannot handle such long recordings, and we still need to find stitching or clustering methods on EEND results. This is our Diarization system. This system is simple and is a typical pipeline which contains VAD, segmentation, embedded extraction, and clustering. We do not use any fusion strategy here. In the following slides, we will describe each part in detail. For the VAD module, we adopt a self-attention-based VAD to detect speech and non-speech parts. This model contains two multi-head attention layers to grasp long dependency. The module is trained on CSSD training set, and the unintelligible words or dialects are also considered as speeches. The loss function is binary cross entropy loss, compared with the baseline VAD that is trained on TDNN and LSTM. Self-attention-based VAD gets rid of almost half of false alarm errors. We also conduct an ablation study in this model, and we find that as the VAD threshold goes higher, detection error also goes higher, and the CDER on the evaluation set goes down. We think this phenomenon is consistent with the design of CDER. CDER is sensitive to false alarm speakers. For the embedding extractor layer, we adopt ICAPA TDN to extract speaker embeddings. The block diagram of the ICAPA TDN model is shown in the left part. ICAPA TDN is an enhanced version of the standard TDNN, and ICAPA means emphasized channel attention, propagation, and aggregation. The detailed design of the architecture can be found on the original paper. After analyzing short duration speaker verification, which is short for SDSV challenge, we found that compared with X-vector or resonant-based models, ICAPA TDNN shows superior performance on short duration utterance, which satisfies the motivation of this challenge. To train the ICAPA TDN model, we adopt on-the-fly data augmentation with additive noise, wrong reverberation, and spectrogram augmentation. And the loss function is AAM softmax loss with a margin of 0.2. Most verification experiments are trained on ISCSLP2022, which is shown in this column. We conduct another two dataset setups, Experiment 2 and Experiment 3. Dataset in Experiment 2 contain additional 3,000 speakers from CSLP, and the EER on VOX10 is 0.97, which is slightly worse than VOX2 because of the language difference. Dataset in Experiment 3 utilized all speakers with over 10,000 speakers, and we adopt this model to conduct the final evaluation. We also conduct an ablation study on segmentation length and minimal segment length. For segment length, although a short segment length can bring better time resolution, we found that segment length with 2 seconds perform the best result. We think this is because the tolerance for training speaker embedding are longer, and segments of short duration will lead to ambiguous speakers. For the ablation study on minimal length, the result shows that bending the segment less than 0.93 seconds is efficient. For those 2 ablation studies, we think reducing false alarm speakers is crucial to improve the final result. For clustering methods, we compare 2 classic offline clustering methods, including agglomerative hierarchical clustering, which is short for AHC, and spectral clustering. Finally, we adopt spectral clustering methods as the final clustering methods. The main pipeline of spectral clustering contains 5 steps: calculate similarity metric, refinement operations, build a Laplacian metric, determine the number of clustering by eigengap, and key means on eigenvectors. The detailed configurations are shown in the red text, and the comparison result is shown in the table. In the final slide, we make a summary. Our system adopts self-attention-based VAD, E-kappa TDM-based embedding structure, and spectral clustering. Compared with the baseline system, our result improved a lot, which is shown in this table. From our STEM, we found that E-kappa TDM shows a strong ability in extracting speaker embeddings. Second, we also find that parameters should be carefully fine-tuned for CDER metric. In the future, we think there are still 2 aspects to be explored. First, to make the best of the CSSD dataset, for example, temporal information, and train an efficient end-to-end model. A simulated diarization dataset for vox syllable and CN syllable may be considered, which can be used for pre-training. Second, the short phrase in this challenge is not solved explicitly, and a more efficient model to extract the short phrase remains to be explored, especially when the segment lasts less than 1 second. That's all. Thanks for listening.